Okay, on this video lesson, we're going to use what we learned yesterday about parametric equations and also what we learned earlier about vectors to model motion. Okay, so a lot of these words you're already going to know, especially those of you that are in physics, but I just want to make sure that we all are using the same terminology. So first of all, when I mention the projectile, that is the object that is launched. That could be a ball, it could be an arrow, it could be really anything, okay? The trajectory is the path of that projectile, which is typically an upside down parabola, but it definitely could be something else depending on the situation. And the range is going to be the horizontal distance a projectile travels. I don't want you to get this confused necessarily with domain and range. Okay. So it says to find parametric equations to model the path of the projectile, we're going to resolve the initial velocity into horizontal and vertical components. Now you actually did this, those of you who are in physics. You did this, okay? This is vectors, basically. But for those of you in physics, a lot of times you just memorize what you need to do and are not connecting it to the math that you already know. So remember with vectors, our horizontal component is the magnitude of the vector times cosine of theta, and the vertical component is the magnitude of the vector times sine of theta. Now the horizontal speed, which is unaffected by gravity, we need to make sure we understand this. This is the magnitude of the horizontal component, like wind, okay? But most of the time in these types of problems, it is actually not going to be wind. It's going to be the speed from which, the initial speed from which the object is launched or thrown or hit or shot or whatever. Okay, and the horizontal distance is going to be its speed times time. And so if you look at this x value right here, this is your horizontal distance. This is the magnitude of the vector, okay, times cosine of theta times your time. So it's the speed times the time. The vertical distance is very similar, except that we have two different things going on. We have the sum of the distance due to initial velocity, okay, this initial velocity which is affecting the horizontal speed, but also the vertical speed. And we've also got gravity to deal with, okay? So notice that this is, the magnitude of the vector, sine theta times t, very similar to the horizontal distance, except that it's sine. But then we're also going to add in to what we got with gravity. Now this is plus 1/2 gravity times time squared. Where gravity here could be in negative 9.8 meters per second or negative 32 feet per second squared. And both of those should be actually per second squareds. I always realize that when I'm looking at this and never fix it, so I apologize. Those should be squareds right there. All right, now these are not the numbers you're used to dealing with. You're actually used to negative 4.9 or negative 16. I think in physics mostly you use this number right here because you're mostly in meters. And so it's the half of that. And this is where we actually get a negative 4.9 is because it's half of gravity, which is a negative acceleration. All right, so then it says if a projectile is launched at an angle of theta with the horizontal, this is like your reference angle, and that's why we use that in our vectors. It says with an initial velocity of v, then the path is described by, and so here we have two equations. So what does this look like? Hopefully you're thinking, hey, this is parametric equations. You've got your horizontal, and you've got your vertical. Okay, now one quick thing that I want to add is that you actually could have a third thing that you're adding here, and I want to just put it in. It's not technically part of the equation, but definitely you need to consider your initial height. Now we don't really have to think about this too much with the horizontal because we usually just think of horizontal, 0 is where you start. All right, but initial height, this is important because if it's dropped off of a building or thrown off of a building, or you shoot an arrow at waist height or something like that, well then that's going to change your initial height. And so you're going to have to compute that in. okay? If they don't give you an initial height, you would assume this is 0, and you would never assume it's more complicated than what they tell you. Obviously, t here is time in seconds, and g is the acceleration due to gravity. Now, this whole concept about acceleration's relationship with velocity is something that you should be getting better at understanding. You started talking about this even back in Algebra 1. You did simple scenarios of this. In physics that you talk about it, even if you're not taking physics AP, in your science class when you've done the physics of problems, you've talked about this idea of acceleration. And then in this class, next year when you take calculus, you should be able to thoroughly understand the relationship between gravity and acceleration and velocity and all of that. This should just be something that you're just getting better at and understanding more and more. You're not going to understand it all right now, inside and out. If you do, that's great. You're one step ahead. Okay, so let's just get an example done because this is how most people learn. So we've got a football player. He kicks a ball with an initial velocity of 82 feet per second at an angle of 65 degrees with the horizontal. After 1.5 seconds, how far has the ball traveled horizontally and vertically? All right, and then what is the total horizontal distance the ball will travel? Now, with just knowledge of Algebra 2 and basic physics, before you did vectors in physics, you really could only work problems where it deals with the vertical distance with time. Now we can work in the horizontal distance, we can work in the angle, we can be much more specific about our problems. So I don't want you to think that we're just doing the same thing we've done before. There are so many more problems we can answer now with this knowledge. Okay, so let's pick out the information that they give us. They give us this initial velocity to be 82. Okay, so that's like our v. It's really like our magnitude of v, but I'm just going to go ahead and label it as v. And then our theta here is going to be 65 degrees. Okay, so let's set up, just to start out, our parametric system almost of x of t and y of t. Now remember, x of t is the horizontal component, and this is going to be our initial speed times t times cosine of the angle. Now I don't know why, but a lot of people leave out that t, and it's right there in the equation, so don't forget that. Okay, our vertical component is going to be very similar, except that it's going to be sine of 65 degrees, but also what we're going to do is we're going to add in 1/2 of our gravity times time squared. Now you got to decide, am I using negative 9.8 or negative 32? Now in this case, since the units have already been established as dealing with feet, I'm going to put in negative 32 here. Okay, so what you can do right now is think, okay, this is plus 1/2 times negative 32. All right, what we're going to do instead is write this. I'm not actually going to cross this out, but I'm going to write this as minus 16t squared. Okay, and I think if you can go straight into that, that's perfectly all right. Okay, so that's, that's like our two parametric equations. All right, now they're giving us a time here at 1.5 seconds. How far has the ball traveled horizontally and vertically? Well, all they're really asking us to do here is to find x of 1.5. All right, they're saying when t is 1.5. Okay, so this is just what is 82 times 1.5 times cosine of 65 degrees. And this, you're going to have to approximate this. This is going to be, something you round to 3 decimal places. So in our calculator, let's just I'm going to wake mine up. Let's make sure my calculator is in degrees mode, because that's 65 degrees. And let's type it in. 82 times 1.5 times cosine of 65. And there we go, 51.982. And our units here are going to be feet. And I'm going to go ahead and put in the word horizontally after it, just to be really specific with my answer. All right, now the next part, they're asking us for the vertical distance after 1.5 seconds. And so again, we have 82 times 1.5, but sine of 65 degrees, and then again minus 16 times 1.5 squared. And we're going to see what this equals. And use your calculator on this. Now I'm just going to hit second enter, bring this back up, make that a sine, and then minus 16, 1.5 squared. And I get 75.476. And that's going to be in feet as well. And I'm going to put vertically after that, just to be really specific with my answer. Okay, now the next question they're asking us is, what is the total horizontal distance the ball will travel? Okay, so when they're saying total horizontal distance, let's think about what this means. Okay, a football player is going to kick a ball, is going to go up in the air, and it's going to come back down. All right, and so if we think about this in terms of how we used to do this problem, let me graph this up here. We used to make it where time was the independent variable and all we did was the vertical component. Okay, we didn't have a horizontal component. So this is another question we would not have been able to solve before today. All right, but what we got to do is we got to think about what we know. All right. And so if I'm looking for, and I already told you there's parametric mode on your calculator, but we're not actually going to use that. That's overcomplicating things and it's going to cause a lot of problems. So when we're thinking about total horizontal distance, let's first figure out how long was the ball in the air. And so once I can figure out this question, well then I'm going to treat it just like I did the last one, except instead of 1.5 seconds, I'll know how long the ball was in the air, and I will plug that into my x of t formula. Okay, so let's use our y of t formula, okay, and let's figure out when did this ball hit the ground. Okay, and this we're going to do the same way we did back in Algebra 1. So what we're going to do, I know that we're trying to answer a horizontal question here, but our horizontal x of t does not tell me how long the ball was in the air. I need to look at the vertical one and figure out, well, when does the height come back down to 0? So let's type in 82t, and I'm not in parametric mode right now. I'm doing all this in function mode, just using what I know. Okay, and so let's go ahead and set our window manually. I'm thinking that this ball is probably not in the air more than 10 seconds. We can go back and change that though, definitely. And then I don't care too much about negative numbers on any of this, but maybe go back and change that to -5, just so I can see the axis. And then the y max, I'm going to guess that this ball is going to go, I don't know, 50 feet up in the air. I could be wrong on this. All right, and so let's hit graph and let's see what happens. Now, I was wrong on it, and I kind of knew that as I was doing the problem. But that's really not that big of a deal because I'm not thinking about what is the maximum of this ball. I'm really thinking about how long it was in the air. Now, if I had to guess 1, 2, 3, 4.5 seconds or so, but if I wanted to find it exactly, there's two options. I can do the second trace as 0, or what's easier and what I know we've practiced at least once this year is to go ahead and plug in 0 into y2, which will graph the line. We don't see it, but it's right on the x-axis, and second trace 5. And I'm going to make sure that my cursor is closer to this one. I don't want it to find the first one. And so I can see that this ball is in the air exactly 4.645 seconds. Now, I've talked about this in class, but I'm going to show you one more time how to store values. Right now, because I just found that intersection, that's stored in for x. Okay, it won't be though as soon as I do something else. But for right now, that is stored in for x. And so when I'm thinking, okay, I answer this 4.645 seconds. Okay, and I use the vertical component to answer that question. Now, okay, I'm going to talk about the horizontal component, and I'm going to find x of 4.645. Okay, this is going to be 82 times this number. Cosine is 65 degrees. When you do this in your calculator, if all you do is type in 82 and then round that number right there, you are losing accuracy. So what we want to do is either hit second answer, or we want to hit X because it's stored for X, or if you want to store it in for another letter, be my guess. All right, and we get 160.965. 160.965 feet. And that's the most accurate answer. Okay, now let's look at the next problem. Here we have an archer shooting an arrow with an initial velocity of 60 meters per second. Notice that we're in meters now. Okay, and we've got an angle now at 4.8 degrees with the horizontal at a target 70 meters away. So this is going to give us something about our horizontal distance at the end. If the bow is held 1.4 meters off the ground, so this is going to be an initial height, how far off the ground will the arrow be when it hits the target? Well, okay, let's just go ahead and write our two equations. X of t is going to be 60t cosine of 4.8 degrees. I'm just using the formulas from the front. And my vertical component is going to be 60t sine 4.8 degrees. All right, minus half of 9.8, which is going to be 4.9 t squared. If this was in feet, I would do minus 16t squared. And then I need to go ahead and add in my 1.4, all right, which is my initial height. Okay, so then they're saying, how far off the ground will the arrow be when it hits the target? All right, let's think about this. Let's think what makes sense. So when the arrow hits its target, okay, let's think. When the arrow hits its target, that's talking about a time when the horizontal distance is 70 meters away. So I need to figure out what that time is first. Okay, so what I'm going to do is say, okay, well, when the arrow hits its target, the horizontal component will be equal to 70. And let's figure out what this time should be. Okay, so in essence, I'm just solving the equation for t here. So this is going to be 70 divided by 60 cosine 4.8. Now this is not answering the question, it's just giving me that time. Then I can figure out what the vertical distance is. How far off the ground will that be when that happens? Okay, so let's, in our calculator, do 70 divided by, I need to use parentheses here, cosine 4.8. All right, and I have 1.171. And keep in mind, this is also a rounded number, so if I use it, I don't want to just plug in 1.71. I want to get exact, okay? So when I get to the next part, when I get to this next part, I want to find y of 1.171. Okay, I can write it out if I want to, but I'm not going to use 1.71. I'm going to use either the stored value or the second answer feature. parentheses there. Sorry, here we go. 1.171. Okay, so let's think about this. This is going to be 60, and then I'm going to hit second answer, sine of 4.8, okay, minus 4.9, parenthesis, second answer again, squared, and then plus 1.4. Okay, and I get 0.562. They're going to be meters. So my accurate, I don't have rounding error, I have an accurate answer. Okay, so when the arrow hits its target, or when the arrow has gone 70 meters horizontally, which happens to be 1.171 seconds, then the arrow is also 0.562 meters off the ground, which should make sense that it's not going to be that much off of 1.4. Okay, now the next part, what is the maximum height the arrow reaches? This is something we actually could have done a long time ago. Now I have a more complicated vertical, I have something that also depends on the angle, all right, but this maximum height, we can do this in our calculator. Okay, so let's plug in our vertical component, 60x sine of 4.8 minus 4.9 x squared plus 1.4. And again, I'm going to go to my window and I'm going to think what makes sense. Now, I already know that this arrow is, it takes less than 2 seconds to even get to the target. So I'm going to change that to 2. And my Y max doesn't need to be 50. It only needs to be maybe like 5 at most. You know, maybe a little bit more. We'll say 10. We'll say it does go higher than a person. We'll be on the safe side. And hit graph. So here you can see our arrow. It does have a little bit of an arch to it. Now, I'm not graphing the actual path of the arrow. This is not my parametric. This is just the vertical component. So this is not representative of the horizontal component at all. It's the vertical component in time. So I just wanted to point that out, although it didn't really matter in this problem whether you understood that or not. So I want to find that maximum height. So I'm going to use the maximum feature. Now, something interesting is next year in calculus, you will be able to find these maximum and mins based off of a simple algebraic move, but we're not ready to do that yet. But our calculator finds it for us. Make sure you do go all the way to the left and all the way to the right. Don't get lazy here and try to shortcut your way through this, because you might be cutting off the true max. Okay, so I have two numbers here, so I got to think about what they mean. X here is not actually X, meaning horizontal. It's the T, it's the time. And the Y value here is 2.686, and that's the number that I really want, because they're asking for the maximum time. So there wasn't a lot to do for the second part. We did most of it on our calculator. I'm going to draw a little picture here just to show you. That's that right there. Okay, last problem. So on the 7th hole of the U.S. Open, Tiger Woods, at the time we wrote this question, there was no scandal involving Tiger Woods, so this is, he was actually an upstanding role model at the time, estimates the distance to the pin to be 220 yards. His swing provides an initial velocity of 160 feet per second, so V is going to be 160, and I am going to go ahead and change this 220 yards to be 660 feet before that trips me up. It says we've got an angle of 28 degrees, and says determine whether or not Tiger makes a hole-in-one. Assume he is directing the ball straight at the pin, because if he was off, if you're thinking of his line of sight to the ball, if he's off right or left, then obviously that would be a mistake. But we're just thinking simplest case here. So let's go ahead and write our two equations. X of t is going to be 160t. Should be getting really good at this. Cosine of, in this case, 28 degrees. And y of t is going to be equal to 160t sine of 28 degrees. Now this is in feet, so we're going to do minus 16t squared. And it doesn't say anything about an initial height, which makes sense because a golf ball would be on the ground. And the height that the tee offers is minimal. Okay, so what we're thinking about here is what is the time that it takes the ball to get there, and then will he have enough initial velocity to make it horizontally? Okay, so first what I'm wanting to find out is what is the time to the pin? So, or what is the time, I guess I should say not what is the time to the pin, but what is the time that the ball's in the air? Okay, so let's go ahead, because I'm going to tell you the answer to this. There are other ways you could figure this out, but due to the nature of the answer, which I already know, this is the most direct way to answer this problem. Because if he overshoots on his first strike, then it's not a hole-in-one. So let's think about this. Okay, we are going to use the vertical component. We are going to plug in that equation, 160x sine of 28, then minus 16x squared. And again, go to your window. Think about how long this ball could be in the air. It's going to be longer than the arrow, but I'm thinking not longer than 10 seconds. Probably much less than that. The highest the ball is going to go is probably much higher than 10. Let's go ahead and put 100 in. Okay, so this is not showing all three variables. This is just showing the height of the ball and time. And if I want to find how long that ball is in the air, this is like what we did on problem number 1. We need to put in a 0 here. And I can estimate what it is. It's, it looks like it's between 4 and 5 seconds. But if I want to find it exactly, there we go. And so that's the time that the ball is in the air. All right, now if he has more than 660 feet of horizontal distance in this amount of time, then he is overshot. If he has less, then we would have to do more calculations to figure out if he had enough velocity to then get him to the pin, which is actually more than we want. So we're hoping this is an easy no here, because the yes would be very hard to assume. Okay? So this right now, we have this stored in for x. All right, let's go ahead and write down what that number was, or the approximation of this number. All right, now, again, what we're doing here, we use that to find the time that the ball was in the air. But what I'm really concerned about is this horizontal distance. Does he make 660? Is it too far? If it's way too less, all of those things. Okay, so let's think about then what is x of 4.695. So it's going to be 160 times 4.695 times cosine of 28 degrees. And when you do this, don't use 4.695, use the actual number. So remember, just to kind of prove it to you again, here we go. That number is stored in for x, temporarily anyway. So I'm going to use that number, cosine of 28. And this is over 660. If you had rounded here, it could mean the difference between not knowing the answer. So when the ball hits the ground, which is 4.695 seconds, all right, that is more horizontally than where the pin was. So he overshot it. So he did not get a hole-in-one. Okay, so let's mark this down on our so no, he overshot. Again, if this number had been less than 660, you'd actually have to do a little bit more work to say that the answer is yes, but this is an easy no. Okay, bring your questions to class.